In 1972, NASA starts work on a radical new, reusable spacecraft. Its innovative design pushes engineering to the limit.
They had to be light, they had to be reusable, they had to be very powerful.
The Space Shuttle challenges engineers to create a vehicle that must withstand the explosive rigors of launch.
Just that main engine, to get that to work is mind-boggling.
Just as incredible, the incinerating temperatures of Reentry.
You're like in the middle of a blowtorch.
Not once, but time and time again.
A lot of sleepless nights over there.
Against all odds, engineers must strive to make spaceflight routine.
Flying in space is tough and it's dangerous.
This is the remarkable story of the unsung heroes who designed, built, and flew the Space Shuttle. April the 12th, 1981, the Kennedy Space Center, Florida. Astronauts John Young and Bob Crippen are about to risk their lives in a vehicle that's never flown before. Space Shuttle, Columbia.
It was a test flight. We didn't know exactly what it was going to do.
Gone for main engine start.
The shuttle's 3 main engines roar into life, followed by 2 giant solid rocket boosters. And the shuttle leaps from the pad.
And that's when my heart rate went up to about 130 beats per minute.
As Columbia thunders skywards, it's the moment thousands of engineers have dedicated their lives to. The launch of the first ever reusable spacecraft. The Space Shuttle is an engineering marvel. For 30 years, it was the workhorse of America's space program, responsible for some of its most memorable achievements.
And we're separating at about 1 foot per second.
Launching satellites,
Satellite drifting away.
delivering and servicing the Hubble Space Telescope, and assembling humanity's largest permanent outpost in space, the International Space Station. The shuttle's unrivaled array of space firsts rests within an extraordinary feature and an incredible engineering challenge: the ability to fly in space time and time again. For years, the idea of a reusable spacecraft is the dream of early space pioneers.
The capability to launch, maneuver in orbit, and then maneuver inside the atmosphere so that a landing can be made at will.
If you go back and you look at the old science fiction films of the 50s, spaceships were reusable. It was accepted. And that dream was very much alive in the minds of the engineers at NASA.
By the end of the 1960s, NASA has put men on the moon, but it's come at a vast cost. Each multi-million-dollar moon rocket is discarded after launch.
In the case of the rocket engines and the rocket vehicles, they didn't come back. They were throwaways. They burned up in the atmosphere, and those vehicles were expensive.
With budgets for space exploration falling, NASA must find a new solution. One which promises to make spaceflight routine and, ultimately, cheaper.
So you're saying to the engineers, you have a chance to build the world's first reusable spaceship, and it's going to be amazing.
It's a hugely ambitious project, and NASA must persuade the US government to fund it. That means recruiting a powerful ally with a vested interest in space. the US Department of Defense. An eye in orbit is the perfect place to keep watch on America's enemies.
NASA understood that in order to get the shuttle approved, they had to make the shuttle attractive to the Department of Defense.
Seeing the shuttle's potential, the DoD agrees to join forces with NASA. But not without two important stipulations. First, the shuttle must be able to return to a specific landing site after just one orbit.
The DoD guys say, launch, take classified reconnaissance photos, and come back down at the end of one orbit and land back at the launch site. The problem is that while you're doing that one orbit, in that 90 minutes, the Earth is turning underneath you.
Meaning, the shuttle's launch site shifts over 1,600 kilometers eastward.
That means that you've got to launch it like a rocket and land it like an airplane, where you can steer to the proper landing point.
Such versatility is something that's never been attempted before with a spacecraft, but is critical in making it reusable. Aerospace engineer Tom Moser is tasked with the engineering challenge.
As the requirements evolved, we knew we had to have a delta wing like some of the fighter jets.
A delta wing will give the shuttle more controllability when returning to Earth. At the Smithsonian Air and Space Museum, it's possible to see this distinctive shape with Space Shuttle Discovery.
The delta wing gave this vehicle maneuverability to move to the left, move to the right, and it also gave it maneuverability during reentry to make these big sweeping S-turns as it was descending to bring this vehicle home. The wings are doing all the work.
The shuttle's delta wing design promises the flying versatility the military requires. But NASA must also fulfill the second major requirement from the Department of Defense, launching large spy satellites.
We had to carry a very large payload that weighed like 65,000 pounds and 15 feet in diameter and 60 feet long.
The strict military requirements dictate the design and shape of the spacecraft, called the orbiter. To launch it, engineers must build 3 revolutionary rocket engines, fueled by a giant external tank, along with 2 solid rocket boosters, giant reusable rockets, and then combine them to provide the immense thrust needed to lift the heavy payloads into orbit.
So it was huge. The DoD requirements were a big driver, huge driver in the design of the shuttle.
The military's demands create a huge engineering challenge. But having them on board ticks the boxes on Capitol Hill. And in January 1972, President Nixon greenlights funding for the shuttle program.
But this was a new idea, and it was one thing to say it, and it's another thing to actually do it.
Now, NASA and the engineers it will employ face the enormity of constructing one of the most complex machines ever built. California, 1972. With the Space Shuttle's design determined, engineers at Rocketdyne begin work on a critical element of getting the orbiter into space. Its 3 main engines. Fresh out of college, Dan Hausman is challenged to help create a revolutionary rocket engine.
It was very exciting because it was a brand new engine program, and we called it the White Truck to Space. Once a week, we would take the Space Shuttle to orbit and life would be good. That's really not how it ended up. It was a big challenge to get that system to work.
The Space Shuttle main engines will be the most sophisticated ever built. And most importantly, reliable enough to be used time and time again, a demand that's never been made of a rocket engine before.
They had to be light, they had to be reusable, and they had to be very powerful. All those factors combined to make an extreme engineering challenge.
Rocket engines produce thrust by burning propellants. Simply put, the more propellant burned each second, the more powerful the rocket. To increase the flow of propellant, rockets use a spinning pump, called a turbopump, to increase the fuel pressure, ultimately increasing thrust. To lift heavy payloads, the shuttle's engines must deliver well over 4 million newtons of thrust, a staggering amount.
Think of the engineering that is required to make that system alone work. Forget about everything else that's on the vehicle. Just that main engine, to get that to work is mind-boggling.
Dan Hausman and his colleagues know it requires a quantum leap in turbopump technology. Engineering one with a phenomenal spin rate of up to 600 revolutions every second.
Your car engine runs at 3,000 RPM. The high-pressure fuel turbopump ran at 33,000 RPM. And the balance of that has to be perfect.
But Dan's team have an engineering solution. Place a small rocket inside the main engine and use its powerful exhaust to rapidly spin the turbopumps. It's called a pre-burner. It looks good on paper, but on the test stand, the engines catastrophically fail in a fraction of a second.
Those initial tests, the engines came apart quite often, which is not a pretty thing to watch, especially if you plan on using that to go fly.
The problem is a balancing act. If the pre-burner spins the pumps too slowly, the engines won't get enough fuel. Too fast, and the pumps spin to destruction.
It just has to be perfect, a jewel watch. If it's not, it'll come apart. And that's where the issues were, is in turbopumps. And that's why the turbopumps got redesigned a number of times.
Calculating something as complex as the performance of a rocket engine is a breeze with today's computing power. But with the limiting technology of the 1970s, it's a painfully slow process.
But all of our engineering was done on slide rules. There was no such thing as computers. We calculated that all by hand.
Dan's team persist, precisely fine-tuning the turbopumps, allowing each rocket engine to fire without a hitch.
And when those three engines actually all lit and behaved nicely, we all said, wow, that was amazing.
Getting astronauts into orbit requires a remarkable feat of engineering. But getting them safely back is an even greater challenge.
Yeah, you got to have a lot of power to get a spaceship into orbit. But the tricky part turns out to be getting it back through the atmosphere in that process that we call reentry.
To orbit Earth requires a speed of around 28,000 kilometers an hour. But landing a shuttle safely means shedding almost all of that energy to touch down at around 320 kilometers an hour. As astronaut Story Musgrave can testify, this huge deceleration creates a fiery problem.
It's just outrageous. You think you should evaporate in a second. You are engulfed. You're like in the middle of a blowtorch.
Early astronauts return in capsules with heat shields designed to survive only one blistering re-entry. But the Space Shuttle must fly multiple missions, which produces a critical engineering problem.
How do you create a heat shield that can withstand that searing heat and be unscathed so that you can use it again?
For the engineers, this forces a radical rethink. The Holy Grail is a material that can withstand temperatures of almost 1,300 degrees Celsius. Eventually, engineers discover a breakthrough.
In the 1960s, Lockheed, working with the help of NASA, came up with a new technology, and that new technology was made out of silica, just like beach sand.
It's discovered that silica can be used to create a hard, lightweight ceramic with amazing thermal properties, providing an extremely good barrier against heat, as thermal protection systems engineer Martin Wilson demonstrates.
If you heat it up, it tends to cool off very, very rapidly. So you can hit it with a lot of heat. It's very hot very quickly, but it also sheds heat very, very rapidly also. And the back's just cold to the touch.
Silica ceramics fit the bill as a reusable heat shield. But the engineers aren't out of the woods yet. Now, they must find a way of covering the shuttle's aluminium airframe. But it's much larger and more complex than conical reentry capsules. Engineers plan to clad it with thousands of custom-made tiles.
The tiles were essentially all different. Every one had to be manufactured specifically for a particular spot on the vehicle.
It's a painstaking task. Over 33,000 tiles must be cut, fired, and precisely glued. But in March 1979, with its maiden flight just 1 year away, orbital assembler Rockwell International are falling behind schedule. They transport the orbiter from their plant in California to Florida, where the remaining tiles will be attached. But the trip reveals a design flaw, which requires a radical rethink if the shuttle is to make it into space. When Columbia arrives at the Kennedy Space Center on the back of a specially modified 747 jumbo jet, engineers like Bob Seek can hardly believe their eyes.
It didn't look as nice as the advertising brochure would have it indicated. There was lots of exposed skin.
Thousands of tiles are missing. Many have fallen off in transit. It's a shocking realization.
The tiles didn't have sufficient strength to stay on. Means we can't fly. Pure and simple. Could not fly.
So suddenly the engineers had to stop and say, oh my God, how are we going to prevent this from happening to a shuttle in flight?
The shuttle is grounded. NASA scrambles to understand why so many tiles have fallen off. The answer lies with something as small as stitching. The shuttle is designed to flex during the stresses and strains of flight. But attaching tiles to a flexing airframe is a recipe for disaster. So the tiles are glued onto stitched felt pads that absorb the forces, keeping the tiles from cracking.
Tiles are very rigid and very fragile, so the pad allows the tile to move relative to the aluminum.
But on inspection, a startling discovery is made. The orientation of stitching within the felt pads means that instead of absorbing the forces of flexing, the pads are amplifying them. That's why so many tiles were lost in transit. For the engineers, the fix is a daunting realization.
So we had to make the tiles stronger. That kept us awake at night. A lot of sleepless nights over that.
Engineers experiment with how to strengthen the tiles so they'll remain attached to the felt pads. Their breakthrough is painting the bottom with a mix of silica, water, and ammonia, and then baking them. The solution soaks into the tiles, adding extra silica, which sets hard when heated. It's a process called densification.
So it doubled the strength of the tile and essentially did not increase the weight a bit. Did not change the thermal performance. It was a miracle. Well, it was not a miracle, but it was good engineering.
It might be good engineering, but the implications are massive. Thousands of tiles must be stripped from Columbia and strengthened.
Then we had to take them off the vehicle, densify them, and put them back on the vehicle.
Desperate to have the shuttle ready for launch, NASA must expand its tile workforce from 200 to 3,000.
Now you have to call in an army of technicians, like a mobilization in wartime that's got to happen for just this one problem.
It was a schedule nightmare. And we literally counted tiles. How many did we put on? How many did we take off? How many do we have left to go?
More than a year is spent working round the clock to complete Columbia's thermal protection system. The astronauts know their lives depend on the quality of this work.
John Young and I spent a lot of time with the people that were doing the tile work, telling them how much we appreciated the effort they were going through, how important it was. It was your body that was going to be strapped into that thing, and you wanted to make sure it would work.
Fixing Columbia's heat shield ranks as one of the crowning engineering achievements, responsible for certifying the Space Shuttle ready to fly. April the 12th, 1981. Columbia finally stands poised for its first test flight. Preparing to board are Commander John Young and pilot Bob Crippen.
Flying in space is tough and it's dangerous. It was a test flight. We didn't know exactly what it was going to do.
Chief Shuttle Engineer Bob Seek is in the firing room.
Yeah, there was tension, apprehension, but on the other hand, there was confidence that, hey, done the best we can.
The anxiety was high, extremely high, because we had two of our colleagues on board.
T-minus 10, 9.
The astronauts ready themselves for the flight of a lifetime.
I turned to John and I said, I think we might do it.
6.
At T-minus 6 seconds, the shuttle's fuel pumps spin into life as the engines ignite.
We've gone for main engine start.
That's when my heart rate went up to about 130 beats per minute. I was pretty excited.
It was like something being born. It's saying, look, I'm ready to go.
Finally, as the shuttle's two solid rocket boosters ignite, Columbia surges from the pad.
I mean, you get up and move, you clear the tower in a couple of seconds.
The engineers in the firing room can hardly contain their excitement.
There's this initial shout of joy from the control room, a big roar. And then we all remembered our discipline and there was immediate quiet.
Roger, go for SRB 7.
After a bone-jarring 2 minutes, the mighty solid rocket boosters are spent.
We see SRB set flight. Roger, on a 7.
Another big roar. And then another, oops, remember our discipline. Quiet.
Negative seats. Columbia, you're negative seats.
At that point, it gets really quiet. You're not shaking anymore. It's about as calm as me sitting here in this chair.
Finally, 8.5 minutes after launch, Columbia's 3 main engines shut down, having performed perfectly.
Euphoria reigned. High fives, hugs, handshakes, tears, flag waving.
There probably wasn't a dry eye in Firing Room 2. I mean, it was just an emotional experience.
After almost a decade of engineering toil, Space Shuttle Columbia arrives in orbit. Engineers and astronauts are ecstatic, but it's short-lived. As the astronauts open the shuttle's payload bay doors, they're greeted by an alarming sight. Missing protective tiles, which could spell disaster for their safe return to Earth.
When I opened up the payload bay doors, I saw that we had some tiles missing. It did cause a lot of consternation on the grounds.
We have a few tile missing. Roger, Grip, we can see that good.
Unmistakable black patches reveal where tiles from the spacecraft's heat shield have torn off. Luckily, they're missing from a non-critical area on the top side of the vehicle.
Now, that part of the shuttle is not a real cause for concern because it does not experience the really intense heating during reentry. But what no one knows is, are we also missing tiles underneath the shuttle where a missing tile could be catastrophic?
During re-entry, Columbia's underside will experience searing temperatures of almost 1,300 degrees Celsius. Tiles lost from here pose a significant threat to the astronauts' survival.
If a tile was missing, there was no way to repair it, there was nothing to do.
The fate of Columbia's astronauts will only become clear when they re-enter the atmosphere. April the 14th, 1981. After a near textbook 2 days in orbit, Columbia begins the final critical part of its maiden flight. Slamming into the atmosphere at over 27,000 kilometers an hour as it returns to Earth.
It's about Mach 25 when you hit the Earth's atmosphere at around 400,000 feet.
As Columbia begins to experience the blazing heat of re-entry, all thoughts are on the orbiter's thermal protection system.
That was a scary moment.
You know, who knew if this thing was actually surviving re-entry?
Didn't know if it would burn through or what.
Enveloped in a searing shroud of plasma, radio communications with Columbia are lost for a nail-biting 16 minutes.
Hello there, Houston, Columbia's here. Hello, Columbia, Houston's here. How do you read?
But right on schedule, communications are restored. And the relief in mission control is palpable.
It was only when that call came through that everybody could breathe a sigh of relief.
Columbia's heat shield survives re-entry, and escorted by 2 chase planes, the orbiter glides towards a landing at Edwards Air Force Base in California's Mojave Desert.
No rattling or shaking, just as smooth as can be, but like you coming in a commercial airliner somewhere.
It was a moment.
Wow, this thing works. It's great. It's a super machine.
For the first time in history, a spacecraft has been launched as a rocket and returned as a glider, a reusable vehicle ready to fly in space again. The success of Columbia paves the way for a new era in spaceflight. NASA rolls out 3 more orbiters: Challenger, Discovery, and Atlantis. Deftly demonstrating the shuttle's ability to carry a wealth of scientific experiments, satellites, and commercial payloads into orbit.
Here comes the chute. Direct chute.
For a while, it seems spaceflight has become almost routine.
T-minus 4 minutes and counting.
Great talkback. Copy that, thank you.
January the 28th, 1986.
We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Roger, roll, Challenger.
God, no.
1 minute, 15 seconds. Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Immediately, we know there's been a tragedy. We know that 7 lives, have been lost.
Just 73 seconds after launch, Space Shuttle Challenger disintegrates in a devastating fireball.
You can't help but think, what happened? What did we do? What did we not do? What step did we miss in a procedure?
Immediately after the disaster, many engineers suspect the failure lies with one of the shuttle's most complex components, its main engines. But engineer Dan Hausman knows it's too early to jump to conclusions.
We were told it was an engine failure. Then I said, that could have been. Don't know. Until we look at the data, we don't know.
Hausman and his colleagues meticulously pore over every millisecond of data returned from each engine.
Now, those engines, they were working just like they were supposed to.
Leading them to a more surprising conclusion.
I quickly realized that it was an SRB issue.
The 2 solid rocket boosters, SRBs for short, help lift the shuttle off the pad. Firing for just over 2 minutes, they're the largest of their type ever built. They draw on tried and tested technology, and compared to the main engines, their design is relatively simple.
I never considered that the booster would ever cause us a problem, because the booster really had no moving parts.
But analyzing film footage of Challenger's launch suggests otherwise.
First indication you got was a film of the launch. You see a puff of smoke when we ignite the boosters.
The footage provides investigators with a vital clue.
Hardware talks to you. It was trying to tell us we had a bad joint design from the very beginning.
The solid rocket boosters are stacked from a number of segments joined together. Inside each joint are flexible rubber bands called O-rings. On ignition, pressure inside pushes on the flexible rubber O-rings, forcing them to seal each joint. But the black smoke caught on camera suggests an O-ring seal has failed. Engineers need to understand why a catastrophic failure occurs during this launch compared to the previous 24 successful launches. The team redoubles their efforts.
On the morning that we actually launched Challenger, it was cold.
If you go look, there was ice on the pad.
The night before launch, temperatures plummet to around -5 degrees Celsius, almost unheard of in Florida. Investigations discover that at these freezing temperatures, the rubber-like O-rings become brittle and fail to seal the solid rocket booster joints as designed. This leads to the devastating chain of events with Challenger.
So what you actually have is something that looks like a blowtorch. You got 6,000 degree gas going over both O-rings and out into the environment.
A little over a minute after launch, searing exhaust from the breached O-ring burns through the SRB's lower strut, causing it to pivot into the giant external fuel tank, which ruptures, cascading tens of thousands of liters of fuel into white-hot exhaust.
It was certainly not a day we should have gone flying.
The loss of Challenger is a huge blow for NASA and the engineers.
After Challenger, there's a lot of us wanted to quit. We didn't want to be part of a program that cost people their lives. We didn't want to be a party to that. And so they brought people in to talk to us and say, you know, we need you guys to help work so that doesn't happen again. And so some people quit. You know, they just couldn't handle that. And so the rest of us just worked very hard to make sure it wouldn't happen again.
Engineers redesigned the SRB joints and O-rings, adding triple redundancy with heaters that will keep them at a constant temperature.
Some people thought that was a belt and suspenders, but it made me feel a lot better to go fly.
September the 29th, 1988. After a comprehensive engineering review and with hundreds of safety modifications, Space Shuttle Discovery heralds a return to flight of America's manned space program. The next 15 years sees the shuttle once again prove itself as an engineering marvel. But its sheer complexity means the odds are stacked against it. February the 1st, 2003. After 16 days in orbit, Columbia and its crew are on their way home, blazing through the atmosphere at 25 times the speed of sound. Then, just 15 minutes from landing,
COG in it.
Mission Control are unable to establish radio contact. Unknown to them, Space Shuttle Columbia has disintegrated in the skies above Texas.
Columbia, Houston, UHF comm check.
Eventually, NASA's worst fears are realized. The loss of the orbiter and another 7 astronauts. For NASA, losing a second shuttle is devastating. But the most likely cause makes it even more unbelievable.
Okay, everybody.
No data, no phone calls, no transmissions anywhere off-site.
Film footage reviewed after launch reveals a piece of foam insulation falling from the external fuel tank. It strikes the leading edge of Columbia's wing.
This is the leading edge of the Delta wing. It's made of a reinforced carbon, and it's actually a cap that fits over the edge of the wing. It takes the highest heat of all during reentry.
It's during reentry that Columbia is lost, suggesting its protective heat shield of reinforced carbon-carbon, or RCC, may have been breached.
We really didn't think something that was as light as a feather could break something as tough as RCC in half.
But as engineers begin their investigations, the truth behind Columbia's disintegration will become tragically clear. Space Shuttle Columbia's destruction leaves engineers dumbfounded. How could a seemingly harmless piece of foam smash a hole in the orbiter's critical heat shield? Ballistics expert Matt Mellis is one of the engineers tasked with finding out.
We got a phone call from one of the folks at Johnson Space Center. They said, we think that this is an impact problem and we think we're going to need your help.
What they find is disturbing.
So this is a little piece of foam. It weighs 2 grams. This is an example of the test specimens that we shot. It weighs what a sheet of paper weighs. The reinforced carbon, and this is a test sample of that. This is what the leading edges of the wings are made out of. Our test showed that if going fast enough, 500 miles an hour, which is not that fast in aerospace terms, this little piece of foam can cause critical damage to this material, which is tough as nails. So it's an amazing lesson that we learned from that.
The team examines the launch footage to determine exactly where the foam struck. They narrow it down to a specific area, between carbon panels 6 and 9 of Columbia's left wing. Building a replica, they focus on this part of the leading edge. Using a powerful air gun, they first fire foam at panel 6. It remains intact, leaving the engineers puzzled, but a vital clue helps their next test. In the search for debris, investigators find fragments of Columbia's leading edge panels belonging to the wing that was struck.
They began to piece these tiles together and these fragments of the leading edge together. They showed molten material in the area of panel 8.
Most metals melt at extremely high temperatures, the kind experienced during re-entry. Discovering so much melted metal around panel 8 is the breakthrough the engineers need.
That really provided supporting evidence that this foam strike took place in the region of panel 8.
The final piece of evidence comes from the foam firing tests. Engineers now focus on panel 8. And the results are shocking.
5, 4, 3, 2, 1, 0.
A piece of foam ultimately caused the loss of a vehicle and the loss of 7 lives.
Engineers learn from the tragic lessons. But with the loss of 2 orbiters and 14 astronauts, the shuttle program's days are numbered.
The Columbia accident, like the Challenger accident before it, was a very painful reminder that there was nothing routine about flying the Space Shuttle.
July the 8th, 2011. Space Shuttle Atlantis lifts off on the program's final flight. Over 3 decades, 135 shuttle missions chalk up a combined 3.5 years in orbit. Carrying 355 individual astronauts from 16 different countries, and delivering over 1,500 tons of payload. But ultimately, the shuttle's complexity means the running costs and risks are too high to continue flying. Today, the shuttles reside in the Smithsonian's National Air and Space Museum and other exhibits around America. An inspiration to all who come to see them.
You can't fly a vehicle like this and not appreciate the handiwork of everyone that was involved in it.
The accolades that those people deserve, it's just an absolutely incredible, amazing feat.
They did what it took to keep this remarkable flying machine in service as the icon of America's aspirations in space.
The shuttle's work is now complete. But its engineering legacy will outlast those who built it. Of all things with wings, the shuttle has to be the most magnificent flying machine of all.